Hello, this is Mr. Gieske. I'm going to help you learn how to use the STO button on your TI to prevent rounding error. The STO button is located right down here on your calculator in the lower left portion above the ON button. I guess this video also explores several other aspects of solving equations and such, but I guess it presumes a knowledge of rounding. So, 5 and above round up and 0 to 4 round down. I'm going to use the law of sines and the law of cosines in an example problem later, and that's going to assume that you know the order of operations and how to solve equations. So if you're not sure about those things, you might want to just prepare yourself or go review those first. The other good news here is that I get a chance to review some different kinds of numbers with you. So let's review the difference between rationals and irrationals. I'm going to divide the rationals into two categories, those that terminate and those that repeat. So numbers that terminate and are rational are numbers like 1/2, which is equal to 0.5, or 3/8, which is 0.375. And numbers that repeat are numbers like 1/3, which equal 0.333 ... which people tend to write as 0.3, repeating. And other number maybe like 4/9, which is 0.444 ... or 0.4, repeating. Or there are more complicated ones such as 2/7, which on your calculator look like 2857142857. I know there's a 1/4 at the end, but if you look at your calculator screen, this 1/4 don't show up because you've used the digits of the calculator. So this is going to go on, which is the same thing as 0.285714, all repeating. Okay, so terminating decimals, or sorry, rational numbers that in decimal form terminate have an endpoint, have a last digit. Repeating ones don't have a last digit, but they follow some pattern. Both of these fall under the rational numbers. For more on that, you can look up a video on that. Irrational numbers, on the other hand, numbers like the square root of 2 are equal to 1.414213562, say your calculator, but really they're only approximately equal to any kind of decimal expansion because they go on forever and ever without repeating. So I hesitate to use the equal sign with these types of numbers. Likewise, pi is approximately equal to 3.141592654. These are the digits that your calculator gives you, but it's not a complete expression of that number. E is another well-used, very common irrational number, 2.718281828. Looks like it repeats in 18281828, but I know that it doesn't. Your calculator is going to make it look like it's going to repeat, but in fact it does not. Likewise, any logarithm of a number that's not a power of the base. So if we're doing base 10, if I pick any number that's not a power of 10, say 16 or 81 or 6,000,003, I'm going to get an irrational number, 1.204119983. That goes on forever, it doesn't repeat. Likewise, any trigonometric evaluation or trig function of an angle that's not a friendly angle, 73 degrees. What constitutes friendly is another conversation. But the sine of 73 degrees is approximately 0.95 563 04756. And that number will go on forever and not repeat. So the reason I'm bringing this up is that these two groups of numbers over here on the left side, sorry, on the right side, the repeating decimals and the non-repeating, non-terminating decimals. So these are non-repeating and non-terminating. These guys often get cut short. They get truncated or rounded prematurely while you're working on a problem, thus creating an error in your final decimal approximation. A lot of times students choose to write 4/9 as 0.4 or 0.44 or 0.444, all of which are not equal to 4/9. A lot of times students write the square root of 2 as 1.41 or pi as 3.14, thinking that those two things are the same when in fact they're not, and as a result you get an error. And even students who are quite savvy get stuck when they go to pick up their calculator and try to evaluate something that involves pi or the square root of 2, and they don't know what to do with all those decimals. And do you round it in the middle of the problem to write it down more easily, or what do you do? So that's what I'm trying to help you understand right now. We're gonna explore the STO button on your calculator. So I think a good example of this is to try to find the parts of the following triangle. Let's say you're given a triangle with the following three sides. You have a side 12, you have a side 15, and you have a side 23. We'll call this angle A, we'll call this angle B, we'll call this angle C. And the goal here is to try to figure out the values of those angles. You might recognize right away that these angles are not going to be friendly, but maybe not. You know, we'll work with whatever we can here. Okay, so those of you pre-calc students who've covered this material so far, you would say, okay, we're going to use a law of cosines. And the law of cosines is really a generalization of the Pythagorean theorem. So we have a non-right triangle, and we have three sides, and we're going to use the law of cosines to find, let's find angle A. So it works like this. 12 squared is equal to 15 squared plus 23 squared minus 2 times 15 times 23 times the cosine of angle A. That's the law of cosines, and I'm going to use this to find the value of A. First I have to solve for the angle A. I'm not going to do any computation until the final step. That's just how I like to do things. So I'm going to express this as the cosine of A is equal to 12 squared minus 15 squared minus 23 squared, all divided by negative 2 times 15 times 23. And then I'm going to write the value that A is equal to the inverse cosine of 12 squared minus 15 squared minus 23 squared, all over negative 2 times 15 times 23. This is just how I do things. I don't pick up the calculator until I have to, and I'd like to type the enter button once. So here I go. Second cosine, give me the inverse cosine. I have a numerator that is a 3 terms, so I need to put those in parentheses. 12 squared minus 15 squared minus 23 squared, close the numerator, divide, and I have a denominator that is made up of 3 factors, so I need to enclose those in parentheses as well. Negative 2 times 15 times 23. Close the denominator, and then I need one more parenthesis to close the inverse cosine. Hit enter. What did I do? see my mistake. Oh, I get to teach you the insert button here as well. So I can go up here, and I need to insert a minus sign here. Second, insert, and notice the cursor changes from a flashing box to a flashing underline. And I just hit the minus sign in the wrong place. Let's try that again. I need to insert it in place of the 1. There we go. Okay, so now I should be able to hit enter, and I get my angle measure of. Now, how do I write this down? I'm gonna write it down in all of its decimal glory here. 27.8641831. 27 point. I've already forgotten. 8641831. 8641831. And you know, somebody else might approximate that as 27.864 degrees, or 27.86, or 27.9, or maybe just 28 degrees, depending on what your teacher wants. But what I'm going to do here is I'm going to preserve all of the decimals that the calculator gives me, knowing that this is an irrational number. And if I cut it off too early and then use this number to find, say, angle B or angle C, I'm going to lose some of the decimal approximation, or decimal accuracy. So I'm going to use the STO button, and I give it a name, and I'm going to call it A because it's angle A. So if I hit STO, it presumes that I'm going to take the answer, STO as A, and hit enter, and it just shows me that the decimal is now entered in as the angle A. Okay, so we go back to our problem, and I say, okay, I know angle A, it's 27.864 degrees roughly. How do I find angle B? That's going to involve the law of sines. And then to find angle C, I'm just going to do 90 minus A minus B. So let me switch over here and try the law of sines. Okay, so the law of sines says that sine of angle A over the opposite side, which is 12, should equal the sine of angle B over its opposite side, 15. Okay, so now instead of writing 27.86 something, I could just call it A for the rest of the problem, knowing that my calculator knows what A is. So if I solve for angle B by saying the sine of B is equal to 15/12 of the sine of angle A, and that B is equal to the inverse sine of, now I'm going to simplify the fraction 15/12 into 5/4 the sine of A. Now I can just pick up my calculator and say that the inverse sine of 5/4, which is 1.25, but I'll call it 5/4 sine alpha A, close the sine, close the inverse sine, and now I've got an expression for B, approximately equal to 748. Okay, so 35.748. 35.748. I believe it was 0614. Let me just check. Sorry, 01694. See, working memory, 01694. Okay, those are degrees, and your teacher might expect you to truncate that or round it or something, but I usually do 3 decimal places rounded. That's 748. Okay, now what I'm going to do though is, because I still need the accuracy of angle C, I'm going to stow this guy as angle B. Call it just B. And now my calculator knows that whenever I type in the letter B, that irrational number in all of its, not all of its glory, but as much glory as the calculator can give me, will always be remembered. And then I can find angle C is equal to 90 minus A minus B. And I can write that out by simply just doing 90 minus A minus B. And we have 26.38779996. 26.38779996, which I would expect my students to write as 26.388 degrees. Okay, so let's review. Initially, I just want to describe to you the difference between rational numbers and irrational numbers so that you would get an idea of which numbers you get into trouble with on your calculator. I would say the terminating decimals, as long as you express them completely without rounding them, you're in good shape. Repeating decimals, you're better off expressing them in their fractional form, 1/3, 4/9, 2/7, instead of their decimal form, because unless you write infinitely many decimals, you're going to truncate the number and not get exactly 1/3 or 2/7 or 4/9. So you can express them in rational form, no big deal. But you still run into trouble if you have decimals. Irrational numbers pose a bigger problem because many students prefer decimals, and you see that there's no comfortable way to write these non-repeating, non-terminating decimals without losing some accuracy, and your teachers are going to prefer that you use pi, e, or root 2 instead of 1.41 or 3.14. I'm asking you to be a little bit more sophisticated in the way you think about some numbers so that you can avoid truncating them and losing error. And the way to do that is really to use algebraic methods to solve equations. But when you get into something complicated like the law of sines and law of cosines, and there's no really comfortable way of expressing 27.864 degrees except in this big bulky mess, but you can do a bit better by just stowing the number in all of its calculator glory and proceeding with at least 7 or 8 decimal places instead of just 1 or 3. And it also saves you the hassle of having to write out all those decimals. So that's it. I hope that helps. Try using the STO button. Saves a lot of time. Okay, here I've got a simpler example, just basic geometry that might help you practice the STO button in an easier context. So let's say the circumference of this circle is 24. And the question is, what is the area? Okay, now a long time ago, prior to calculators, we would do the problem as such. You would say the circumference, which is equal to 2 pi r, is equal to 24. And you know that the area of a circle is equal to pi r squared. So if we can solve for r in the circumference problem, and then take r and substitute it into this equation, we can find out the area. So let's just do that. R is equal to 24 over 2 pi, which is equal to 12 over pi. And then we say the area is equal to pi times 12 over pi squared. And that means we have pi times 144 over pi squared, which is equal to 144 over pi. Okay, so that all works, and the area is equal to 144 over pi. So if these are, say, inches, then this is in inches, and this is in square inches. Okay, 144 over pi, 144 over 3 is about 50, a little less than 50. This is going to be quite a bit less than 50, but something a little bit less than 50. So I will pull up my calculator. Let's move it over here. And we'll see that 144 divided by alpha pi, second pi, is 45.836 approximately. So this is 45.836 inches squared. Now the real area is 144 over pi, The approximate area is 45.837 or 836. I should call that 837. The mathematician wants to say the area is 144 over pi, but if somebody said how much paint can you fill in that circle, and you said 144 over pi square inches, the person kind of look at you funny. If you said approximately 46 square inches, that would be a more understandable answer. So on one hand, I like the precision of 144 over pi, but I think the approximation is serves the reader well. Now, what about the STO button? Well, I see a lot of kids getting the R value, 12 over pi, typing in 12 divided by pi, and approximating that right here, and it's calling that, R is equal to 3.82. Now that's a problem. I mean, first of all, we recognize that R is approximately equal to 3.82, and that's not equal to 3.82. And the second problem is that you're truncating this number right here, or rounding it, and so you lose all of this information here. And because this number is a little bit less than 3.82, when you square it over here and then multiply it by pi, you're gonna what's called propagate that error. You're gonna square the error and then multiply the error by pi, which is gonna make the error larger. So, for example, if we do pi times 3.82 squared, we should get something like 45.837, but we don't. We get 45.843. Our rounding of 3.8197, which is 3/10,000ths away from 3.82, turned into an error of looks like about 0.06. So that's 6/1000ths. Sorry, 6/10,000. So our error grew by a factor of 6. And that's a problem, especially when you're dealing with small tolerance and you're a physicist or an engineer, and you don't want to lose that error, or you don't want to create that error. So if you must approximate the radius, let's say you do want to know what the radius is, and you say the radius is roughly 3.82 inches, what you can do is carry as much of this information as you can about that radius, divided by pi, and you store it as R, alpha R. You can store it as any letter you like, but R makes sense because it's a radius. And so now we have all of those digits stored as R. And if you do pi R squared, you'll get the same number that we had over here, 45.837. 8366. It's the identical number. We haven't lost any error, or haven't created any more error because of the calculator. We have created a little bit of error in the rounding, but we've preserved as much accuracy as the calculator can provide for us. So I hope that makes sense. What I'm going to do is I'm just going to put a little red line through that. You don't want to approximate a number too early and then go and use it, because you'll just create an error. It is helpful to approximate numbers, but it does lead to premature rounding leads to sort of propagation of error. So just be careful with that. So I hope that that works for you.